let me start right now with that. So I think we're on the time anyway. Yeah. So she asked me to go over this state sum definition of the Alexander polynomial. So this is going to, for Alex, state sum for both Alexander and Alexander Conway, depending on what weights you choose. So the weights for Alexander are essentially the ones in his original paper, which I note this way, and this means for the weights, for our purposes, slightly different weights than Alexander, but the same structure. We're going to have a T for this, a T for this, a 1 here, and a 1 here. Those are the weights for Alexander. I'll explain in a moment how I use this. And then for Conway, weights are S inverse 1 and 1 for positive crossing, and S inverse S 1 and 1 for negative crossing. And then the way this works is you have a diagram. Say you have the trephone model. I'll be doing it twice, but here's a diagram with an A, and then that inherent in the diagram are the states, right? I mean, both the states and the labels and the weights. If I draw the diagram, then I know what the weights are, but I also have states, of which I'll just draw one. I choose two regions to get my states that I'm going to sum over. I choose two regions that are adjacent to one another, and I eliminate them from the running. And then let's orient it so defense. And then a state is a choice of between crossing and region, so that each region has one crossing chosen. Well, I think of a region as choosing a crossing, right? So this region chose that crossing, this region chose that crossing, this region chose that crossing. And then the relation between the diagram and the state is that this is equal to the product of the weights marked by the state, product over, that's for each state, and then take the sum. Well, no, there's no sum. Yeah, this is just the definition of this. So for the given state, you take the product of the weights that are marked by that state. So in this case, what would that be if this is this state and here's K? Then in this case, what is KS? Well, you look at this state and you look over here and you see, let's suppose we're doing Conway, all right? We could do Alexander just as well. But if we were doing Conway, then we're going to have S here and S inverse here. We're going to have S here and S inverse there. S here and S inverse there, all the crossing positive. And I didn't draw the ones. So those are local weights, right? At a given crossing, you see those weights. So here we have an S, here we have a 1, and here we have an S inverse. So therefore, this is S times 1 times S inverse, which is 1. That's the KS, right? The evaluation of the norm with regard to the state. And then the polynomial is equal to the sum over the states of the KS times the sign of the state sign of the state. And the sign of the state is equal to the parity of the number of black holes. For a black hole is a marker that goes in between two ingoing lines. No intent to actually match this with physics. Perhaps somebody will match it someday and then we'll all be surprised, but I called it a black hole for memory's sake, right? So I look at the state and I ask, how many black holes do you have? And this one has a minus. So then in this case, the Ks sign S is equal to -1. Here. So that's the form in which this state sum lives. Now, last time when I was talking about it briefly, I was explaining that this comes about by some good accidents combined with looking carefully at Alexander's original definition of the Alexander polynomial, where he was computing a determinant, and his determinant could be thought of as products of certain things times the sign of permutations. And when I stared at it a long while ago, for a long time and tried some things, I realized that I could do it entirely combinatorially in a state sum like this. And that's a nice model, particularly for the Conway. If you want the Alexander, you say the same thing, but you use T's and you use these weights. So it comes to the same thing. So why don't we do just Conway and write it out for this polynomial. So then I'm going to do Conway for the trefoil knot. And the trefoil knot is easy to work with because these are all forward S's, backward S inverses, right? The crossings are all positive. And there are 3 states. And we can work out what their contributions are. Okay, so there are 3 copies of the diagram, and now what about the 3 states? Well, here's one. Here's another. And here's a third. And if you play around with it, you see that's all there is, right? You're supposed to have each region choose exactly one crossing, have a marker at one crossing, and there are only those 3. Now, I said some other things, but that I won't repeat unless you want me to talk about that. How if you smooth the state, you get a unicursal drawing that lets you walk through the state without crossing any crossing, get a Jordan curve. And that the states are in one-to-one correspondence with the trees in the checkerboard graph. So they have a very nice interpretations combinatorially, and that's of interest. But if we just wanted to compute the polynomial, then we're all ready to do that. All we have to do is look at this and see what we have. This is an S, this is a 1, and that's an S inverse, I'll write bar. This is an S, this is an S, that's a 1, and this is a 1, and that's an S inverse. This is an S inverse. And what about the sign? Well, how many black holes are there here? One, so that's a -1. How many black holes are there here? None, so that's a +1. And how many black holes are there here? 2, so that's a -1 squared. So now I've decorated the states with all of the weight information that I have to sum to get the polynomial. And then I conclude, therefore, that the polynomial, if we call it the triple non-K, is equal to 1 minus 1 from this one. And this one is S squared. And this one is S to the -2. And you might note that this is equal to 1 plus S minus S inverse squared. Did not. And that's 1 plus C squared. And that's the sense in which this is Conway. For Conway, the Z is S minus S inverse. So to obtain the Conway polynomial, you work this out and then you will find out that it actually is a polynomial in S minus S inverse. And that's the Conway polynomial, and I wrote this mistake. Okay, so that's the algorithm. And then there would be many exercises to do to understand that this is working. You would want to prove that it's invariant under the Reidemeister rules. But the combinatorics is set up in such a way that that won't be too hard to do, actually. You have to think about, well, what are all the states that are nearby the Reidemeister, right? You have to think about that. You have a Reidemeister group, say you have a Reidemeister 2 move, and then what kind of state markers could there be? Let's suppose that the stars, the eliminated regions are far away for the sake of this argument. Well, then you might have a marker here, and you might have a marker here. That's possible. Or you might have a marker here and a marker here, and so on. So corresponding to this, there is a list of local states. And with the help of what is the list of local states and how do they behave, you can puzzle it out, and you'll find that the contributions will cancel out in the right way so that you're going to get the same result as that. Okay, just like when we worked with the bracket and we found out that things canceled out if we chose things in the right way. So, and then of course it's a more complex exercise to do the 3 moves, and the 1 move is very easy altogether. So this is the state sum, and maybe that answers your question. Okay. There's a lot more to say about this, but I wanted to mention it because it's interesting and it's related to the history of the original Alexander polynomial, in that he defined it combinatorially, and then things went on in a different direction and people didn't look, or at least I don't think anybody really looked combinatorially at Alexander until Conway came along. And then Conway looked at it and saw, we should mention, you see, Conway's formula. Conway somehow saw that formula in terms of, perhaps in terms of a formulation of Alexander's original definition, or maybe he saw it some other way, but he saw this formula, and in this form, this is all normalized exactly right. So this actually is a model for which this is true. And as long as I'm talking about it, let me show you how that comes about, just for the heck of it. But anyway, this is interesting historically, in terms of more recent history and older history. It's probably the first time somebody wrote down a combinatorial state sum model for an out polynomial. And then a couple of years later, we realized we could write state sum models for Jones and the other polynomials. But why does this happen from this? Okay, let's talk about that. So we have this formula. And I could write this formula out symbolically. This way, I could say, well, if you have a crossing, then I'm going to get S times, and now I'm going to write a marker here, and this means sum only over states with a marker like this. Okay, so then there are also the states with a marker like this. Only the plus sign is not right anymore because I have to put a minus sign because I'm ignoring otherwise. Ignore the marker indicated. So I'm peeling off the code information that the marker contains. And if the marker had a black hole in it, then it had a minus sign in it, right? So I'll pull that minus sign out as well. And then you're just looking at this as a symbol for those states which have a marker there. Okay, but that's not all. Then there's also what happens if there's a marker up, and what happens if there's a marker down. And those, of course, received a 1 in our weights. So this is a way of saying the same thing as S inverse with a minus sign there, which corresponded to the black hole. Right? I'll put the minus sign there for the sign. And this formula now displays it sort of like the bracket as a sum of things. Okay. And then we can say, well, what would happen if I switch the crossing? Well, if I switch the crossing, then that will turn into an S inverse. Turn into S. And otherwise, everything remains the same. Well, now you have it kind of in front of you, so you can think about it. What would happen if I took the difference? If I take the difference, these sums of states cancel each other out. They have the same coefficients, and they're the same anyway. They're just the same states altogether. But these are different, and so I get a difference formula. And my difference formula reads that this minus this is going to be equal to S minus S inverse times the forward marker. I'm subtracting, so I get S minus S inverse times the backward marker. So I get S minus S inverse times the states with a forward marker plus the sum over the states with a backward marker. But the states of the smoothing link are in one-to-one correspondence with the set of states where you would close it up and put a forward marker here, union the set of states where you would close it up and put a backward marker here. Now, maybe you need a picture in order to see that, but let me say it anyway. Suppose you had a state of this. Then the question you have to ask is, where's the marker in this region? Here's the region. Well, the marker might be over here. Or the marker might be over here. On one side or the other of a dotted line connecting these two. If there's a marker over here and you would like a state of the crossing diagram, then you need to put a marker here because there's no, if you made two regions out of the one region here, then there's no marker in this region. So you need to put a marker here and that will create this. And vice versa over there. And that may not be clear to you, so let me just show you an example and then I think it will be completely clear. Let's take this guy here. Right? Versus a smoothing of it like this. So this is where I have this and I'm comparing it to this. And I want to draw a state of this that corresponds to this state. So I have a marker here, I leave it alone, and I have a marker here. And then that's it. I just remove this and I have a marker. Because you see, what happened when I smoothed it was that I joined these two regions into one region, and the marker for this region on the left became the marker for this whole region, right? And vice versa. If I have a state here and I pinch this together, then I have an empty region, but that empty region has a marker forward because it had a marker on the left over there. So this works as long as the region isn't an annulus or something, but that has to do with the cases and I want case checking and the fact that the Conway polynomial vanishes when you have disjoint loops. So there are a couple of little technicalities in there about that you could ask about. What about that region, this region here? Maybe this region goes all the way around like that, but that's where things turn into zero. It has to do with the fact that the Conway polynomial is zero on disjoint lengths. So there is that, but assuming that this is one region where this makes a distinction in that region and makes it into two. And that turns out to be the only case I actually need to think about. That's what I'm saying. Okay. So given that this dotted line really does separate that region into two regions, then the argument I gave you is correct. And that means that this sum here is actually equal to the state sum for the link obtained by smoothing out the crossing. And there's the Conway formula. Okay? So that's how it comes about that this is a model for the Conway. Okay. Other questions? Okay, I have a bit of recreation and then we're going to go back and talk about Kauffman for that. But here's my recreation. I said to you before that if you draw a link diagram and always draw it under, before, over, then a knot diagram or a link diagram, then you'll get an unknot. So Here's a related thing, which is interesting recreationally. I'm going to have a little robot. I have a dot diagram on it. I have a little robot, which I will denote by well, we're going to have a little robot, but I'm loath to keep drawing his face all the time, so I'll just draw his face right here. This robot's face. And this robot has the following rules. An unnodding robot, I think. This robot moves along the diagram, and if it's an overcrossing motion, you don't have to give him any other, just a dot. And if he moves across an overcrossing line, nothing happens. If he goes under something, then he switches to crossing. Switch. Nothing. Okay, those are the rules for the operation of this robot. He just does that local thing. He doesn't see the diagram as a whole at all. Just walks along the diagram, and the robot walks around the diagram once. Okay. So shall we do this? So the robot goes along this diagram, and the first step that he takes puts him here, and nothing happened because it was an overcrossing. Then crosses the next one, and then it's an undercrossing. So he's here, and this crossing got switched up. But he's going to go all the way around the diagram. So the next time it's no effect. He ends up here. Next time under, so he has to go over. Next time over again. Here, now he's here. And the last time over. Two unders. And under. Over. Now he's back home. Of course, the diagram is unknotted, but you may not see that this will always work, but I claim it always works. So this is the robot's progress. It starts here, goes along like that. My claim is that this robot, if he does this turn around the diagram, will always end up with an unknotted diagram. Maybe we want one more try before we leave the subject of the robot. I'll leave it to you to prove that the robot does this. Take somebody who's a little more knotted. Let's see what would be a good knot. Okay. Maybe just the figure 8 knot as the next example, right? So let me try doing this by erasure if I can. I'll take another copy of the figure 8 here for reference. We'll start the robot there. So now the robot goes here and ends up here, right? Good enough. And at that point, the robot will disappear from here. This crossing will get switched over, and the robot ends up here. Watch me because I'm doing it by erasure. It's going to be bad. Now, no problem here. It's over. So it disappears here and reappears there. Okay, next one's under, so we're going to have to switch that crossing from over to under and put the robot here. Now it's hitting another under crossing, so we'll have to switch that over. Put it here. Better done on a real blackboard, isn't it? And then he's going to switch this crossing and up here. And now he's going to switch this crossing. And up here. And one more crossing switch and we're done. Interesting to see whether we've made some mistake or not. Over. Worked out. Came back to where we started, and the diagram is unknotted. Any ideas why this robot should be working? It's a very ignorant robot, right? He doesn't do anything but do something locally. He doesn't know anything about the large diagram, but yet he manages to unknot the large diagram. Can you explain why it works? I assert it does work. I mean, you might be searching for an explanation for something that doesn't work. That wouldn't be good, but I tell you, believe me, it works. Has to be a good reason. Well, I'll leave it to you to think about that. Try it out. Try it out. It's easier with pencil and paper and a little bit of erasure than it is on this blackboard where we have to keep alternating that way. Let's see, one more recreation if we have the time. I think I'll do it now rather than later. No, I think I'll do it later. We can do it right at the end. I was telling you about Kauffman phonology, and I want to go back and explain where that comes from. But my point of view on it, there's more than one point of view on this because it's using an extra kind of structure in relation to the bracket for our purposes. One way to think of it is that it's a way of asking the question which naturally occurs to anybody if they're working with the bracket. You've seen that the bracket can do various things. It can tell mirror images apart and so on. And there's this combinatorial state sum. And somehow you'd like to understand how the states behave in some global way in order to get at something deeper about what's going on. And so that's really, in a sense, what Kauffman did. And let me use my slideshow to indicate a couple of things that will save us a little time. So if you were looking at the Trephlonon and you wrote down all the states of the Trephlonon, then here they are, written in a kind of a funny way, because I want to think of this and this as being corresponding to one another, although this is up a little bit and that's down a little bit, but think of pulling that down a little bit. And then this is the A state of the trefoil knot, right? If you have a trefoil knot and you are thinking about A and B states, right? Then the A smoothing of the trefoil knot is this one. And the B smoothing of the trefoil knot is this one. And if I take the all A smoothing of the trefoil knot, then I'm going to get this guy. And then I can continue looking at all of the states of the trefoil knot by saying, okay, I'm going to look at the first one and I'm going to smooth it to a B. Or I'm going to take the second one and I'll smooth it to a B, or the third one and I'll smooth it to a B. And then I get a column of single B smoothings, and then I get a column of double B smoothings, and finally I get a column of triple B smoothings in the case of the trefoil. So I've organized the states in that way. And then I'm going to put an arrow from one state to the other if I go from an A to a B. So this is an organizational arrow that says that if I started with an A here and I re-smoothed it, get a B, and I put an arrow in there, and then that generates this organizational device generates a big arrow diagram of states. From a link diagram okay. And in the case of the trefoil knot, there's our diagram of states, all 8 states, but now organized in this way, all A, 1B, 2B, 3B. That's helpful. Even if you weren't doing anything else and you were just trying to think, well, how do the states contribute to the polynomial like we were talking about last time, then this is helpful. And the arrows are helpful. But Kovanov had a larger theoretical idea. And his idea, as I said, is to think of this as a category. And then if you're thinking in categorical terms, there are ways to measure how a category behaves as a global object. And I'm going to talk about that a little bit. And then apply that idea, cohomology of a category, to this category and get cohomology groups or homology groups that you can compute that will turn out, if you're lucky, and he was lucky, or appropriately very highly intelligently lucky, to get it to be invariant under the Reidemeister rules. And so you have an invariant of knots, which is not just the polynomial, but are these homology groups that are associated with this category. And then from that, you can retrieve the original polynomial. But I want to get into that subject a bit with you. It would be nice to have another 3 weeks or something. But it's interesting to just for you. I hope it's interesting to just get an introduction to this. It takes a while to get used to it in any case, and there's lots of features of it. So if you just look at what kind of a category, category. So last time I didn't even write down the axioms for categories. So let's write them down so we have them. Category C is equal to a set of objects, so-called objects, and I'll write nodes as well, because you can think of it like a graph and a set of morphisms. And so a category might look like this, might look like here's a node and here's another node, and here's an arrow between them, and here's another arrow to this node, and maybe there's an arrow going all the way back to the original node, and then maybe there's an arrow from this one to this one, and from here to here, and from here to here. And these have names. This arrow is A, this arrow is B, this arrow is C. The objects have names. Maybe this object is called capital A, not related to the A. They're in capital B and capital C. Then these ones have special names. They always do. They're called the identities associated with the objects, and I'll explain in a moment. But what I've just drawn for you is a category. I have to give you the axioms, and you'll see that it can be a category. But it's just a directed graph. That's what I've told you here. It's a directed graph. There are nodes. There are arrows that go. Oh, I didn't say that morphisms, each morphism has a head and a tail in the objects. So one can write arrow going between A and B like that. But it doesn't mean that there's a function from A to B. It just means there's an arrow between node A and node B. Just a directed graph, that's all. By this time, I have told you that it's a directed graph. That's the definition of a directed graph, right? A graph with oriented edges. But then, axiom number one, given A going by F to B and E going by G to C, there exists GF going by A, C composition. There exists a well-defined arrow that is the composition arrow of these two arrows that I just drew. And from this point of view, what category is about is thinking about compositional structure. And of course, you have compositional structure all over mathematics, on compositions of functions and other things that you can plug together. And you have it in combinatorics as well, where these are not necessarily functions. So in this case, if I told you that C is equal to the composition of B and A, notice I'm writing it the way we compose functions. That's customary. A goes, when you have a function from A to B and another function from B to C, you write B composed with A to denote the function from A to C. And it is customary in categories to use the order of composition of functions where you compose on the right. Somebody might say, I'd rather write AB for it, and they could if they wanted to, if they told you what they were doing. So that's the composition of arrows. That's good. Secondly, every object A has self-arrow identity sub A going from A to A, and composition with identity sub A does nothing. So in other words, if I took C composed with, I will sometimes write, sometimes I will write E composed with F. Sometimes I will just write GF. G composed with F, but G composed with F could be our definition of that operation. So if C composed with 1 sub A, that'll just be the same as C. That's still an arrow that starts in C. I'm sorry, it starts in 1 sub C. Oh, that's the way I wrote it, but that's not very, I'm going to leave that out and use different letters because otherwise this. Suppose I have an object A. An object A. I have the identity morphism for A, the identity arrow for A, and then this goes to B by F, all right. And then I have the identity arrow for B as well. So then what I say when I say does nothing is that if I started in A and I did the identity arrow for A, and then I did F, that's still going from A to A, and this is the same as F. On the other hand, I could take the identity on B and run it on the result of doing F. And that takes me from A to B, and that will be also equal to F. So this is what I meant by does nothing over there. Okay. Acts like the identity. And then third, and very important for this structure, is composition is associative. Composition is associative means that if you had I'll illustrate that here. If I did this and this and this, F and G and H. And there are two ways that I could get to an arrow from here to here. I'm not drawing the objects, pardon me. Let's just draw the two pictures that I can get, F and G and H. All right, so maybe I take the composition of F and G, GF. And then I compose that with H. Then I get H, GF, composing it that way, in that order. First GF, then H. Or I could compose G and H, getting H, G. And then I could compose with F. That would be F, H, G. An arrow from here to here. And axiom 3 says that composition is associative. It says that they get the same arrow. Of course, with functions on sets, that's exactly what happens. With functions on a set, then it's associative. Other operations in mathematics are not associative, but for the definition of a category, it's assumed that the compositions are associative. And so this guy here is a little category, given that C is equal to the composition of A and B. And you can think of other small graphical categories. Let's look at a couple of them. Suppose I had one object and an identity morphism on that object. There's the smallest category possible. The identity morphism composed with itself is just the identity morphism, and nothing else is happening. Done, right? It's category. What if we had the identity morphism, however, and some other morphism F on this single object O. Well, now you have a lot more. You have the identity on O. You have F. You have F squared, F cubed, F to the fourth, and so on, and potentially an infinite number of arrows in this category. I may draw just a little graph like that, but if I really wanted to draw what the category looked like, it looks like this. I got this identity arrow, and then it's got F, and then it's got F squared, and then it's got F cubed, and so on. And there's this infinite onion of morphisms that are sitting there going from that node to that node. So this category is infinite, even though the graph is very simple. On the other hand, if I told you that I had this category where I have objects A and B and a morphism F from A to B, and we have the identity on A, and we have the identity on B, then this is finite. The morphism set here is the identity on A, the identity on B, and F. That's all there is. Here it's infinite set of morphisms. Here it's a finite set of morphisms. Every directed graph gives you every directed graph generates a category. Nodes C of G. The nodes of C of G are equal to the nodes of G, the objects of C of G. And the morphisms, or the arrows, that's straight arrows, of C of G are equal to identities of A arrows for each node A of G. Okay, we need to add them. Have to put in the identity arrows if they weren't there before. Union all paths on the graph, all directed paths on the graph. So you might have a graph like this. It's going to be a finite one. And let's call these two sets I and J, all right? So we know what I is going to be. It's just going to be one little morphism for each node. But what about J? Or maybe I should call it P. Would be better. The identity parts and the path part. So what about the path part? Well, for the path part, we're going to have, of course, the identity paths. So I guess I do have to put them in. We're going to have, non-identity other than the identity. Other than identity. I just wanted to throw them up there so I didn't have to worry about them. Well, the other paths are, of course, the individual A, B, C, D. original edges. And then you have to look at the graph and ask, well, what kind of paths can I get? I could go, for example, AE. That's a composition. That's a path from here to here. And so that's EA. And then I could go DEA and end up here. Or I could go CDEA. They are like this. Infinite CDEA. Then having gone CDEA, I could then go ED, EDA, and so on. And because I have a cycle in the graph, an oriented cycle in the graph, there'll be infinitely many compositions around that cycle. And other things are going on, right? So I'm going to get a whole slew of composite morphisms that have to do with the path structure of the graph. But nevertheless, that's one way to get a lot of categories, because you start with a graph and you take the paths on that graph and you end up with a category. Okay? There are other categories that are more related to just global mathematics. You can have the category, and then you name a field of mathematics, sets, or groups, or topological spaces, and so on, like that. And when you think that way, which is the way the original category theorists, Eilenberg and MacLean, were thinking at this level, they're thinking I have all topological spaces, and I have some method of getting a group out of a topological space, like the fundamental group. So I have a way of mapping from the category of topological spaces to the category of groups by taking the fundamental group of the space. And that mapping from one big system of mathematical objects to another is called a functor, taking one category to another. But each of these is a category. What are the nodes and the arrows? In the case of, say, topological spaces, the nodes are spaces. So a dot in the directed graph corresponding to this category of topological spaces represents any topological space. That's a huge graph, not a little tiny one like this. And a mapping from one topological space to another, an arrow from one space to another, is a continuous mapping. So then if you map continuously from one space to another and then to another and compose them, you get a new continuous mapping, and it's associative. And so you have a category. So the category definition, being as simple as it is, applies to huge numbers of things. And so almost any field in mathematics it can be thought of as a category, and then you can consider ways of mapping one category to another. So if you have a category and you have another category, then you can consider a mapping between categories. Maps between categories are called functors. It's just a function from one category to the other, but it's called a functor, so you know you're talking about a map of categories rather than just some function. And it must, of course, preserve structure, just like any other good map of one mathematical structure to another. What structure is there to preserve in a category, or if you were mapping a category to a category? Well, you'll have to map nodes to nodes. You'll have to map edges to edges, morphisms to morphisms. And you want it, and so the main thing is that f of g composed with f should be equal to f of g composed with f of f, etc. I'll say. That's of course the main one, that compositions should be preserved under the mapping. And a good example of that from this way of thinking is fundamental group takes spaces, groups. And we didn't study fundamental group, but I did mention it and show you how to compute the fundamental group of the complement of a knot. But it has the property that if you have a map from one space to another, then there's an induced map on the fundamental group, because loops can be mapped to loops by the continuous mapping from one space to the other. And when you do that, it preserves this kind of structure, composition, and mapping. And so goes from spaces to groups. And that's a functor. So what we're going to be looking at here is categories in this arena, where we're thinking of a graphical structure and thinking of it as a category, and then asking what kind of structure can we put on that category. So look at this as a category now. It's just a graph with, these are the nodes, and these are the edges in the graph. And just think of these as nodes, and then it looks like that picture in the upper part of the diagram. It looks like a cube, where we have 3 A's at one end and 3 B's at the other end. And as we go along an edge in the cube, we change an A to a B. Okay? So that's the structure of this category. And all the arrows are going from left to right. So you can think of, so there are lots of more morphisms than we had before, more than the edges. For example, this composition is a morphism, and this composition is a morphism. And this composition is a morphism. So on. And then it's a finite number of compositions involved, because there aren't any closed directed cycles in this graph. So this is a pretty small category. It's just a finite number of compositions that are involved. Not as huge as some of the examples that we immediately thought of, like this guy here. If I start with this directed graph, I get a countable category. If I start with this directed graph with 2 morphisms going to a point, I get an even bigger, not cardinality bigger, but a lot more things. Compositions of F and compositions of G and ordered differences. But, so this is not such a big category from that point of view. But I want to now talk about why we're going to do something that looks like homology with regard to a category that we have in front of us. So the first thing is something that I mentioned last time, and that is, if you have any category at all, then you can think of simplices in relation to the morphisms. If you have a single arrow, well then you can think of that as a one-dimensional simplex. If you have 2 arrows, I claim that you can think of a 2-dimensional simplex associated with them. And that's just as obvious, because you have 2 arrows, A and B, and then you have their composition, okay? And all together, they form a 2-dimensional simplex. If you had 3 arrows, and they're composable, 3 composable arrows like this, then you can compose these 2. You get BA. And you can compose these 2. And you can get TB. And then you can consider the triple composition, which is ABCBA. I don't have to write parentheses on that because the category is associative. And I get a 3 simplex that corresponds to a composition of 3 things. So if you have F1, F2, Fn, and they're composable, so you think of F1, F2, Fn, like that, then this n-tuple of morphisms, this n-tuple of edges, can be thought of as an n-simplex. The generalization. So if you formally, when we think about n-dimensional simplices, higher and higher dimensional simplices, we tend to do it this way. We tend to say, oh, I'll put the endpoints as 0 and 1 for this one, and the endpoints as 0 and 1 and 2 for this one, and the endpoints as 0 and 1 and 2 and 3 for this one. So if I wanted to do that, I'm probably making my indexing a little weird if I start with a 1, but nevertheless, n things give you an n simplex. So I tend to write in the abstract 0, 1, meaning a 1 simplex, and I could even have a 0 simplex, and I would write 0 for the abstract simplex. And I would write 0, 1, 2 for this, and 0, 1, 2, 3 for this, okay, and so on. And you can then think of higher order ones without drawing their pictures. And there's a notion of the boundary of a simplex. So for example, if I had this simplex here, and I thought of directing the arrows on the simplex this way, lower number to higher number, then I would say, let's call this delta 2. Then the boundary of delta 2, I think of as 0, 1 plus the 1, 2 minus the 0, 2, because the boundary ought to go like this, right? This way, that way, and then back this way. And if I have just the simple 0, 1 simplex, then the boundary of the 0, 1 simplex is equal to the 1 minus the 0. So in other words, I have an algebraic boundary formula for a simplicity. It goes like this. The boundary of 0, 1 is 1 minus 0. The boundary of 0, 1, 2 is equal to 1, 2 minus 0, 2 plus 0, 1. The boundary of 0, 1, 2, 3 on. So in general, the boundary formula that works well here after a lot of thought by various people over the years is that you take and remove the first one. I'll put a hat on it. Then you subtract, removing the second one. And you add, removing the third one. Subtract, removing the fourth one. You keep on going in that fashion. each one represents a face, right? You remove one of these and you get a face. And it's at the level of the third one that you want to see, you want to draw a picture and see that these are all working right. Now let me show you. I'm going to remove the first one with a plus sign. Then I'm going to remove the second one with a minus sign. I'm going to actually remove them this time. 0, 2, 3. Then I'm going to remove the next one with a plus sign. Last one, minus sign. So those represent the removals. I often leave the removals in. This time I left them out. If you took the 0, 1, 2, 3, and asked, is that a sensible boundary for it? Well, let's suppose that you use 1, 2, 3 as your orientation. So then the normal for that bit of surface is pointing out on that simplex, right? Pointing out. Now, what about the others? 0, 2, 3. 0, 2, 3, if I didn't put a minus sign, would have the normal pointing in, right? 0, 2, 3, and I bring my hand over, and the normal is pointing in. But I need the minus sign, so the normal is pointing out on 0, 2, 3. 0, 1, 3. 0, 1, 3, right, normal is pointing out. And 0, 1, 2, well, 0, 1, 2 would have the normal pointing in unless I put in the minus sign. So assigning the signs in that way has all the normals pointing out. And then everything will work out right this way. And this is a very nice rule. So the rule is, of course, that the boundary of 0, 1, n is equal to the sum on I of minus 1 I times 0, 1 I remove n. We're writing an algebraic sum to the boundary. And this has the property that boundary equals 0 for simplicity. The simplices occur in topology for lots of situations. I'm saying that if you want to think of a category as a kind of a space and measure it, you can think of it as a bunch of simplices put together, and then use the ideas of how to measure spaces that are made up out of simplices. And so I just shifted here and started talking about how I measured simplices themselves, never mind the categories for a moment. But we want to see that boundary is equal to 0 in a case. So take this one here. The boundary of 0, 1, 2 is this, right? The boundary of 0, 1, 2 is equal to 1, 2 minus 2, 0 and 0, 1. So it really goes around like that. And then the bookkeeping is exactly what you would expect it to do. And if you take the boundary twice, it's going to all vanish, but you want to see it. So let me see it. Suppose that I take boundary squared of 0, 1, 2 and actually work it out. Then I'm going to get the boundary of 1, 2, which is 2 minus 1, minus the boundary of 0, 2, which is 2 minus 0, plus the boundary of 0, 1, which is 1 minus 0. And now, if I'm lucky, it will all cancel out. 2 cancels with minus 2, minus 1 cancels with 1, and minus 0 cancels with minus 0. So this is 0. And so exactly the same combinatorics is working to tell you that if you define the boundary of a simplex this way, then you'll have the boundary composed with the boundary that's equal to 0. And then you're in a position to measure spaces that are made up out of simplices by asking for things that have 0 boundary in them, modulo the things that are boundaries. So that's the idea of homology, and it's a rather late date to be telling you about homology. But if I have X is equal to space made from simplices, then we do the following thing. We let C sub k of the space be equal to the module generated by the k simplices over, say, the integers, integer coefficient. Just like I was writing down before, 0, 1 plus 0, 2. I could write down 0, 1 plus 3 times 0, 2, things like that. And then I define boundary, taking ck of x to ck minus 1 of x by extending boundary of simplex, which we already know how to do. And we define the kth homology group of x be equal to the kernel of boundary, taking ck to ck minus 1, modulo the image of boundary, taking ck plus 1 to ck, which I say in words as cycles mod boundaries. That is to say, let's look at a space. Suppose you had a space like this, for example, where these two simplices are present, and we're concerned with H1 of the space. Right? I would have to orient these somehow. So let's just put 0, 1, 2, 3, 4, and 5, and now they're glued together according to our assumptions about simplices, right? And then this would be susceptible to this definition. But you see that there is a cycle, there is somebody, namely, if I looked at alpha and I said alpha will be equal to 0, 1 plus 1, 2 minus 0, 2, then boundary of alpha is equal to 0. That's what we just worked out before. That's a little curve going around. And alpha is not equal to the boundary of beta for any beta. And alpha belongs to C1 of my space, and beta would belong to C2 of the space if there was one. But on the other hand, we do have that if gamma was equal to this guy here, this 2 simplex, 0, 2, 3, then gamma, boundary gamma, is equal to 0, 2 plus 2, 3 minus 303, right? So this is an element in C1 that is knocked out by this definition. It's not there, right? Here's a nice curve, a nice one cycle in C1, but it's equal to the boundary of somebody, so it's modded out by it. And the only thing that's left, if you did the whole calculation, would be this cycle here. This one is surviving, and all the other cycles, and there are a number of them. There's this one, and this one, and this one, and there's one that goes all the way around, and so on. The basic one that survives is 0, 1, 2 cycle, and that's the homology. So that what you get, if you did the calculation here, in this case here, we would find that the first homology group of our space is isomorphic to Z, generated by alpha. Because we don't just get alpha, we get alpha, 2 alpha, minus 137 alpha, and so on. All those integer multiples of alpha are still there as things that are not boundaries. Okay, so the idea of homology is that you measure the holes in the space. Those are the things whose boundary is 0, kernel. So this is the set of things that that boundary takes to 0. Set of things, set of alpha such that boundary alpha equals 0, modulo the set of alpha such that alpha is equal to the boundary of somebody else. Holes modulo holes that are filled in. So we're getting a picture of what are the holes in the space that way, one-dimensional holes in this space. And higher dimensional holes as well. And that's the original idea about homology, that you would measure a space by looking at the holes in this algebraic way, taking the kernel of a boundary operator modulo the image of the boundary operator. And I don't know whether you've seen homology before or not, but it's a very simple idea, which obviously, once you start working it out, has lots of technicalities. How many of you have seen some homology? What were you going to ask?
Yeah, I forgot. Like the one-dimensional hole, it's full like around a one-dimensional.
Yeah, so I think of a one-dimensional cycle as a possible one-dimensional hole. Right. You can think of other. You can think of lots of examples now. If you go away from this algebra that I'm drawing and just go back to thinking about a space. So for example, if you had a torus and you're looking at curves in the torus, then you have a curve like this, and that is surrounding a one-dimensional hole, right? That isn't bounding anybody. On the other hand, this little guy here is bounding a disk right there. So that's homologically trivial, but this one isn't. And another one that isn't would be this curve here, which doesn't bound anybody. Of course, you have to analyze to see what bounds and what doesn't bound, right? And then bounding isn't necessarily a disk. So if we go back to our situation here, and suppose that I had somebody like this, a torus with a hole in it, right? Well, then the hole in the torus that alpha, that's bounding the rest of the torus, which I can call tau, right? All of this surface. So alpha is equal to the boundary of tau, where tau is the surface above it. So in this punctured torus, this curve here is 0 in homology. It gets knocked out in homology because it's the boundary of this thing. going all the way up. So we aren't talking about just bounding disks, we're talking about bounding anything that can be coherently put together so that its boundary is exactly this. And this could be actually articulated out of little simplices. You know, you could cut the torus up into little simplices so that the torus was indeed a simplicial space. Not hard to do that. So that's what homology is like in ordinary topology. But what happens here is that roughly speaking, it goes like this. You have a category, and you think of the category as like a simplicial complex. Then you can consider the homology of the category. And Kovanov's idea was that if you use this category and you put algebra here on these objects in the right way, then you could take the homology of that category and get something that would be an invariant of a knot. And then I don't have enough time to show you how it works, but part of it is worth showing you the formalism of it, so you could read a little further if you wanted to. All these categories that come up in the knot theory for our knot theory for Kauffman are cubical. They all look like cubes. They all have the same pattern that you start with a bunch of A's. That's the abstraction of some knot with an A state. And then you are going to consider all of these other things. You could turn this into a B and leave these alone, and so on. You could turn the second one into a B and you could leave these alone. And this will go on, and you may have somebody like A, B, A, B over here, and eventually all the way over here, these. And what you're looking at is a general cube. This would be a 4 cube rather than a 3 cube. And if you had 5 of these, it would be a 5-dimensional cube. So it's like the simplices going on. And so you can think of an x1, x2 through xn gadget like this as representing one of these places here, and then its boundary is going to be equal to some with certain signs. We have to figure out what they are, just like an abstract simplex of x1, xj, some choice of j hat, where xj equals a and xj hat is equal to b. This is the analog of a simplex, but it's going to be for the cubical category. It works very well, and you can do it directly rather than working with simplices. So I show you what I mean directly, and you'll see what I'm going to do. I'm going to take the boundary of A, first of all. A. And it's going to be equal to, I changed it to a B and left this alone. But the next one is going to be a minus sign. I changed this one to a B and I left that alone. And the next one is going to be a plus sign, and I changed this to a B and I left that alone. And that's going to be the formal boundary of this guy. Make sense? It's just like simplices. So over here, there would be this one, and this one, and this one, and these look like the boundary of this one, where I put in one B here, one B here, and one B there. And I put in alternating minus and plus signs. and I'm changing to a B. That looks good, but what am I going to do if I want to take the boundary of B, A? Well, the answer is the only way you can do it so that boundary equals 0. If you're going to start here, and that seems like a reasonable thing to do, then what are you going to do here? You're supposed to ignore that B, right? You have to ignore it. And then you meet an A, and it's the A's that tell you about the signs. I'll show you how this works by just doing one. We're going to take this guy and we're going to take its boundary. So it's going to be changing the A to a B, but no sign. And then minus, leaving that alone, and changing this one to the sign is equal to -1 for the number of A's before it, for the place where you change things. Where you change it. So there's nobody here. Here I want to change A, but there are no A's prior to it. Plus, here I have an A, and there is one A before it, minus, and so on down the line. So in other words, you just ignore the B's and do that. So can you do that? Try it out. I suppose you had A, B, B, A, B, and you want to calculate the boundary, formal boundary of that. So it's going to be B, 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 A, B. And then you have to figure out the sign for the next one. Oh, there's one A prior to that A, so it's going to be minus B, A alone. B, B, change this one to a B. I'll underline the one I changed. A, B, and then plus A, B, B, A, B. Okay. So it's easy, it's an easy rule. You just ignore, you look at one of these, and you ignore the B's, and you go plus, minus, plus up the line, right? And then you will find that boundary equals 0. So this is getting a pattern like simplices, but then we're thinking of each of these as being something like a simplex. But what we're saying is that we're going to have it's going to go like this, that associated to state like AAA will have, we will have a module B of the state. Then you're going to have, for example, V of the AAA. It's going to map into the V of the B A. All right. And the other two arrows, sorry. Each of these arrows is going to be a map from a module to a module to a module to a module. And it isn't obvious that this would all work out, but it does. That's the thing. I wanted to just tell you the general pattern of it. What you're going to do is you're going to take the direct sum of these, so that this is one single module, and the direct sum of these and that one. And so then what you're going to have is you're going to have the AAA, the module for the AAA is going to go into the direct sum of the modules the BAA, the ABA, and the AAB. Right, you just put them all together, but there are three maps. We have three maps. And the way, and I'm going to think of this as a boundary map, taking me from here to there. And it's going to be the sum of the three maps. And so when I write this, I really mean the sum of the three maps. So I hope you get the pattern idea of it. See, there's a module here. You have three maps under each of these modules. You can add up the maps if you add up the modules. And then you need to know, how should I add the maps? And you need the right signs, just as though it were like simplest, something like simplest. And so you add these according to the signs I told you. And then over here, there are more maps to go from this direct sum to that direct sum. And you add these maps up according to the signs. And then you find that if you took this composition and did this composition, you'd get zero. So you would have chain complex. You would have something whose homology you could compute. So in other words, what you end up with is you start with the states, you measure them by writing them as a kind of a module. And then you have a way of mapping the states from one to another in such a way that this collection of states maps to that one in a way so that if you compose them twice, you get zero. And if you have something which you can compose twice to get zero, then you can measure the kernel of that divided by the image of that. And that's homology. So you end up finding a way to measure homology with regard to the states in that way. That's what Kauffman figured out how to do. And that's called Kauffman homology. And then the internal details of that are actually very amusing and interesting, how to evolve this definition and why it ends up being invariant under the Reidemeister moves and all the rest. Which we don't have time to go into. But what I was hoping was that if I told you just a little about that much anyway today, then if you were going to look at one of the papers about this, oops, I was going in the wrong direction there, then you would at least have a guide to the general form of it, how it works. Part of it is almost a retrograde bit of algebra, because we're used to saying a plus b cubed, for example, is a cubed plus 3a squared b plus 3ab squared plus b cubed. But what we're paying attention to here is that if you actually divided a cube of side length a and b into parallelopipedes by putting in all the planes, then it would divide into the pieces in that algebra, a bit that's a cubed, another bit over there that's b cubed, and other parts that are a by b squared or a squared by b. And what you're doing when you're looking at the cube category is almost the same as doing a bit of extra algebra on a plus b cubed, as though you put an arrow in there instead of a plus sign. I think I had that illustrated better here. If you have a plus b squared, then it's a squared plus 2ab plus b squared. But what if I took a arrow b squared and distributed as though I could distribute it just like the plus sign, and then distributed products over arrows? Then I would end up with the picture of the cube or the edge of the cube mapping to the other edge of the cube, I would end up, if I play around with it, with the picture of the decomposition of the two-dimensional cube, right? And where the picture of the decomposition of the two-dimensional cube is into those parts. And the same thing happens if you went to 3. And so the category that you're generating, the cubical category, is actually what is inherited from taking A arrow B and taking it to the nth power formally. It's like you kept track of what people threw away when they invented algebra for you. And there's really a lot of structure there, and that structure is in back of what we can do to measure things about the states of the knot. So I'll stop there and hope that you get interested to find out more about this. I'm going to put some more things into the resource part of the course. So if you would look at it in a couple of days, you will find a paper or two about Kauffman homology. You will find, if I didn't already put it there, and you'll find some notes that summarize what we did across the course as well. So thank you very much for listening to all this.
Can you return back when you were talking about orientation on 3 simplex? I was lost in that moment. Yeah, please.
Yeah, okay, let's look at it again.
Thank you.
There's your C3 simplex. And I formally take the boundary of it by removing the first one, keeping this, subtracting and removing the second one, adding and removing the third one, and subtracting and removing the fourth one. That's the simple algebraic rule. Then we can look at that and ask, what does that say? If I had a if I had a 1, 2, 3, 2, 3, like that. And if I've just drawn it here like that, I think of putting a cycle on it like that. That's my orientation on it, 1, 2, 3. And then the normal points this way.
Yes.
In general, that's where the normal points. So then let's go through here. This is a 1, 2, 3.
Yes.
It's in space like that. Like that. So it's normal. Yeah, that's right. And so its normal is pointing outward from the face of the simplex, right? Now, if I look at this one, the 0, 2, 3, in that form, then the normal is still pointing this way, just like this one is. I don't want the normal to point that way. I want the normal to point this way.
And I was like, okay.
That's the way I want it to point. I want to have this object where all of the directions are pointing outward, right? And the reason I want that is because you could think of a bit of plane where you have some two simplices on your plane like this, and you want the boundaries to all be canceling with one another. So normals, whoops, I've got the normals. I wanted them, sorry. I want to set these for normals all pointing upward. So these are all set that way. And if they are all set that way, let's just draw them for a moment and then look at the corresponding boundaries. So you have a simplex and another one with a common boundary. And if the normals are both in the same direction, then the induced orientation on the edge is opposite, which means that when you compute the algebraic boundary of this and the algebraic boundary of that, then these will cancel, right? So that means that if I have all the arrows pointing outward normally, and I compute the boundaries of each of these and add them all up, then these will all cancel out. And since every edge belongs to two simplices, I'll get zero boundary for this. And that will be making sure that the boundary of the boundary is zero, which is what I want. So when I want the boundary of the boundary to be equal to zero, then I want these coefficients to correspond, to all the normals pointing in the same direction at the level of 3D.
Thank you.
And that did happen here. That was the point. That when we got to this one, quite particularly, if I did it in the 0, 2, 3 direction, I'd have the normal this way, but that got the correcting sign. And the other one is 0, 1, 2. The 0, 1, 2 would be pointing this way, but we've got a correcting sign. So that's a beautiful thing. That's an old discovery way back at the beginning of people beginning to do homology theory, that they could get straight the orientations in all dimensions that way, and then it had a simple rule. And so you have these generators for any space, the simplicities, and they satisfy boundary equals 0, and so you can set up the chain complex of a space in general so that boundary would be 0 and measure its homology. And then what I didn't tell you was that from the simplicial point of view, it's very easy to see how in the category you would do the same thing. The way you do it is you have, but that isn't precisely the way Kauffman did it, but I wanted to show it to you because the ideas are so close. If I have something like this, and I want to talk about its boundary, then the boundary is obtained by either, well, in general, the idea of the boundary is to take two of these and compose them. And then you only have two maps rather than three. And those become the boundary edges of the simplex. So we saw it in the simplest case, where I had F and G and GF. And we could call this simplex delta. And the boundary of delta should be equal to F plus G minus GF. But I want delta to be equal to this possible composition FG, right? So then what should the boundary be? And you see that it involves eliminating one of them. You could eliminate one to get a smaller thing at one end or the other, or composing them. And so that's the way the morphisms end up turning into simplices in a general category like that. All I'm saying is that you can read off from the composition of morphisms what the boundary ought to be. If you have more than these, you see what it will look like. You'll have this edge, you'll have that edge, and you'll have this edge. And so if you had F, G, and H, and then this is GF, and this is HG, and this is HGF, right? So then you're looking at F and G and H, and you're asking, well, what should the boundary of that be? Well, if I just took F alone, then I would have the GH simplex, and there it is, right? If I remove the G, then I will have the FH. I'm sorry, if I remove the G, I should have just the FH simplex, and where is it? Where did it go? No, I can't remove the G, I'm sorry. The ones where I can make a single removal are at the end, so I can remove the F or I can remove the H. If I remove the H, then I get the GF part over here. If I remove the F, I get the GH part over here. But then what about this other part? This other part is where I have the HGF and this guy in front, or the other one in back. You can just read them off. That's all I'm saying. You can read them off. And then you can write down algebraically what they are. And what they are without the signs. Remove the F, the GH. Remove the H, and you get FG. Compose these two, and you get GF. H. Compose these two, and you get FHG. And each of these is in there as one of the faces of the simplex that you're looking at. You can see them, right?
Yes.
So that's what I'm saying, that from the point of view of the sequence of maps, F, G, H, K, and so on, for composition, you can remove this one, you can remove that one, or you can compose this one with this one, this one with this one, or this one with this one, and they form the simplices on the boundary. So every compositional sequence gives rise to a simplex structure. And the category can be thought of as built up out of all the compositional sequences that make it. He didn't choose to use that full part of the correspondence in order to define the Kauffman phonology. He used something simpler, but he could have done it this way. The idea was coming. Yeah.
I was wondering about if there's a way of thinking about this idea in terms of about this idea, so associating faces to in terms of algorithm associating surfaces to null, like Seifert algorithm.
Are you asking?
Mm-hmm.
Yeah. So it's a good question. We know what Kovanov did was radical and motivated by the existence of state sums, right? So we have various states, and we're trying to make sense out of how those states behave and so on. And this led to the Kovanov complex and to the homology of his complex and so on, and led to new invariants. There are other things that are natural to do that are not unrelated to these, like forming a surface whose boundary is the knot. And in particular, if you are forming just the checkerboard surface, then you see that the states are related to that already, right? It might not even be oriented the way you grab it, right? You might take this surface, right? You can always take the checkerboard surface like that. And it isn't necessarily oriented, but there it is. And if you take the different smoothings, then that all corresponds to these different states with some extra bits of surface bounding components in the state. So the surfaces are involved. And you may want to look at this surface, or as I said, maybe you prefer oriented surface, in which case you should have chosen a ciphered surface like this. But it's still the case that the smoothings will give rise to other surfaces. And why shouldn't those surfaces be related to what this construction was doing? There is some literature about people trying to invoke the surfaces that are present in relation to this. And it's not obvious beyond what already goes on in the Kauffman homology. It's not obvious what that might mean. But the interesting thing is that it is related, the surfaces are related to the Kauffman homology in the following way. You can think of this mapping, which is formal in Kauffman homology, the way I told you, you just re-smooth. But you can think of that, I should have drawn it the other way because it makes my life of making the next drawing. So let me draw this. So you can think of the association of one smoothing to the other smoothing as filled in by a surface whose boundary at the top has one smoothing type right there, and whose boundary at the bottom has the other smoothing type right there. And I could have extended that to a knot up here and a link or a knot down here, so that there's a surface that goes between them, and the boundary consists of the upper boundary is this knot, and the lower boundary is this knot, and we went from one to the other by re-smoothing it. And then you can think of all of the maps, think of all of these maps in the complex as cobordisms along surface. By cobordism, I just mean a co-boarding. At one end, it's one thing, and at the other end, it's the other. And that turns out to be the right way to think about what those maps are in the complex that we were talking about before. Maybe I have a picture of it. I'll show you. Like that, yeah. So if this was one of the states and you went from here to here, then you see that from this point of view, I'm looking at that. And those surfaces are actually exactly important for thinking about the structure of how this Kauffman homology works. Turns out, we could go into that, but so some aspects of surfaces really are there. It's a partial answer to your question. Something else. I should say that this machinery that I was beginning to describe to you is remarkably successful in that Kronheimer and Moravka, after a while, were able to prove that Kauffman homology detects the unknown. The knot polynomial might detect the unknown. We don't know. It might be that the bracket polynomial of a knot being trivial, being just some power of A, would imply that the knot is unknotted, but nobody knows that yet. It's a conjecture. But it is known that if the Kauffman homology, which is a kind of extension of that polynomial, if that is trivial, then the knot is unknotted. And they prove that by connecting it to a lot of extra mathematical structure do instant on floor homology. And that's related to physics. And so there are a lot of connections here that haven't gone into. I'm glad we got as far as we did, but it would be fun to continue further. We start into conferences next week, so I can't offer a lot of time, but if you're interested in talking about any of this further, of course, I'm available. Just write me an email. Okay, thank you again.